Okay, we have two warm-ups today as well. These are both a little bit wordy, okay? I want you to get some practice reading through and doing these which of the following statements is false kinds of questions. So here's the first one. Please pause and solve. Okay, the answer to this question is D, okay? It says a study examined the relationship between sepal length and sepal width for two varieties of an exotic tropical plant. I don't really know what that means, but that doesn't matter, okay? All I have to be able to do is analyze this scatter plot. Varieties A and B are represented by X's and O's respectively, which means the X's are variety A and the O's are variety B. Which of the following statements is false? Considering variety A only, so only looking at the X's, there is a negative correlation between sepal length and width. Yes, these have a negative relationship. B, considering variety B only, the least squares regression line for predicting sepal length from sepal width has a negative slope. Yes, it does. The LSRL would have a negative slope here if I just look at the O's. C, considering both varieties, meaning both of these lumped together, there is a positive correlation between sepal length and width. That's true, okay? If I were to lump all these together, I would have to draw my regression line like that, okay? So C, awkward as it is true. D, considering each variety separately, there is a positive correlation between sepal length and width. No, that contradicts A and B, okay? We decided that if you consider the two varieties separately, we would have two negative correlations. And then E, considering both varieties, the least squares regression line for predicting sepal length from sepal width has a positive slope. E is saying the same thing that C is saying. Having a positive correlation and having a positive slope are the same thing. The answer is D. Here's your second question. Please pause and solve. Okay, on May 11th, 50 randomly selected subjects had their systolic blood pressure recorded twice, the first time at 9 a.m. and the second time at 2 p.m. If one were to examine the relationship between the morning and afternoon readings, then one might expect the correlation to be. The answer is B, high and positive, okay? The reason for that is exactly what it says. Those with relatively high readings in the morning will tend to have relatively high readings in the afternoon. If you have high blood pressure, you have high blood pressure. It doesn't matter much when you measure it. So somebody that has low, so let's say the x-axis is AM, the y-axis is PM. If I have low blood pressure, I have low blood pressure in the morning and I have low blood pressure in the afternoon. If I have kind of average blood pressure, then I'm average in the morning and I'm average in the afternoon. And if I have high blood pressure, then I'm high in the morning and high in the afternoon, and I have this strong, positive, linear relationship. Okay, so I do expect to see a high positive correlation here. Today is the last lesson for Chapter 3. This is going to be kind of a hodgepodge sort of lesson. Then for the next 2 days, we're going to do some practice and review. And on Thursday of this week, you have your Chapter 3 test. Okay? So in bivariate data analysis, we are looking at the relationship between two quantitative variables. However, there are many other variables that may influence the behavior of the variables we study. In other words, the two variables that we study don't exist all by themselves. There are other variables that are influencing them. And we call these lurking variables. Okay? A lurking variable is a variable that is not the response or the explanatory. It's not X or Y, but it may influence the interpretation of relationships among those variables. Okay? So something that's lurking, it's hiding in the shadows, okay? We don't see it, but it is exerting an influence here. Here is an example. Look at, we're just considering this as our explanatory variable and this as our response. And the explanatory variable is the number of Methodist ministers in New England. The response variable is the number of barrels of Cuban rum that are being imported to Boston. And I can see a clear positive relationship. As this is increasing, so is this. Does that mean that this influx of Methodist ministers in New England is causing there to be more rum imported? Does that mean that the influx of Methodist ministers is driving people to drink more rum? No, it does not mean that, okay? That is not what we're trying to say here. There is a lurking variable. And what is the lurking variable here? Well, look at the time frame. We're dealing with the 1860s to the 1910s. This was a time of extreme population growth. The size of the population in this region is the lurking variable. As the population increases, the number of ministers increases. So does the number of teachers. So does the number of doctors. So does the number of everything, right? Our population is growing. And as the population is growing, our imports are going to grow. It doesn't matter if it's rum. Everything that's being imported, the amounts are increasing because we have a larger population in the area. So X is not causing Y. We have a lurking variable of population growth. So it's important to remember that just because we have a strong correlation does not mean that we have a causation relationship. X and Y can have a really, really strong correlation, but that doesn't mean that one is causing the other. If you just ask yourself, is there something else that could be causing this relationship? Then that will sort of alert you to the presence of a lurking variable. Okay, so just asking yourself, is it really this simple or is there something else at work here? That'll help you find that lurking variable. A study shows that there is a positive correlation between the size of a hospital, measured in the number of beds in that hospital, and the median number of days that patients remain in the hospital. So the larger the hospital, the longer people stay there, is what this is saying. Does this mean that you can shorten your hospital stay by choosing a small hospital? Okay, I don't want to stay in the hospital very long at all, so I'm going to go to a small hospital. Is that how it works, or is there a lurking variable here? Okay, I would say that the most prominent lurking variable here is the severity of the illness. If you are super duper sick, you're not going to go to some teeny tiny rinky-dink hospital. You're going to go to the big emergency trauma center hospital that's huge, okay? And if you're really, really sick, that means you're going to be staying in the hospital a lot longer. If you have a really big paper cut, okay, and you just need a couple stitches, you're not going to drive all the way to the trauma center. You're okay going to the little teeny tiny hospital, and your stay isn't going to be long at all because your illness isn't very severe. So the lurking variable here is the severity of the illness. If we are less severe, then we can go to a smaller hospital and we don't stay as long. If we are very, very ill, then we go to a larger hospital, but we end up staying a longer time, not because of the size of the hospital, but because of how sick we are. The next thing I want to talk about is outliers, okay? In Chapter 1, we had that 1.5 IQR rule. That does not apply here. You cannot do that because we have two variables. There is not a numerical test for outliers if we're dealing with bivariate data. So you know at this point that correlation is not resistant to outliers. One outlier, one stray point, can have a really strong influence on the correlation. Since my data is bivariate, I can have outliers in both directions. I can have outliers in the X direction, and I can have outliers in the Y direction. And some of these exert more influence than others. Here's an example. On the x-axis, we have the age at which a kid says their first word. This is their age in months. And on the y-axis, we have the Giesel Adaptive Score. I'm not sure what that means, but it's some measure of intelligence or something like that, okay? And so on the next slide, we're going to interpret the slope and y-intercept because we need to practice that. But while we're here on this scatter plot, I want to point out two different outliers. The first over here is child 18. Child 18 would be an outlier, I'm down here, in the x direction. It fits the linear model, but it's far from the other data points in the x direction. It has a small residual, it fits the linear model, but it's out here. Child 19 up here, now I'm looking at this part, is an outlier in the y direction, okay? Its x value is not unusual compared to the other children's x values. I have some below it and some above it, but it is way above the regression line. It has a large positive residual in this case, okay? So these two children, child 18 and child 19, are going to be the two outliers that we're looking at here. Child 18 is an outlier in the x direction. Child 19 is an outlier in the y direction. We're going to pause and practice writing the equation of least squares regression lines. No, we're not. We're going to practice interpreting the slope and y-intercept. So for this one, remember x is the age at first word in months. And y is the Giesel adaptive score. And what I want you to do is interpret the slope and y-intercept, please. So I want you to write a slope sentence, and I want you to write a y-intercept sentence, and I want you to ask yourself if they make sense. So please pause the video and do that. Okay, my slope sentence, remember, as x increases by 1, we expect y to increase or decrease by the slope. So as x, the age at first word, increases by 1 month, we predict y, the Giesel adaptive score, to increase. No, we don't. We expect it to decrease because the slope is negative. To decrease by 1.1270. We weren't given units, so I'm just going to leave it like that. On average. So as the age at first word increases by 1 month, we predict the Giesel adaptive score to decrease by 1.1270 on average. Does that make sense in context? Yes, I think it does. For the y-intercept, I would say for a child whose age at first word is 0 months, we predict a Giesel adaptive score of 109.8738. Now ask yourself, does that make sense in context? I do not think it does. There are no children who start speaking at 0 months old, right? Look at my data. The lowest X values I have are around 10 months. This is extrapolation. It is no good, okay? So if you're asked to do this, do it, but then say, this makes no sense in context, all right? We're going to come back now to our discussion of outliers. So looking again at this scatter plot, I have 2 regression lines drawn in, okay? The blue one, which you can't really tell what's blue and what's green. The blue one is this one right here. This is the line that is drawn after removing child 18, okay? So this green one, the one that I didn't highlight, was the original line. And this blue one is the one after child 18 is removed from the data set. Child 18 has an influence on the regression line. Now, I didn't show the new regression line after child 19 was removed because it didn't move it. You can see, you can kind of cover up child 19 with your finger or something, and that green regression line, the original line, is still a good fit. But when you cover up child 18, all of a sudden, the line doesn't need to go quite that far. Okay, so removing child 18 is going to decrease the y-intercept, okay, and it's going to make the slope closer to 0, all right? Because the least square regression line changes after I exclude this child, we call child 18 an influential point. Influential points are typically points that are x direction extremes, okay? They pull the least squares regression line near them. So if I get rid of them, the line kind of shifts back to where it probably should have been to begin with. Does that make sense? So if I get rid of kid 18, it moves the regression line. If I get rid of kid 19, it doesn't really have an impact on the regression line. So they're both outliers, but child 18 is more influential. So an outlier is any point that falls out of the general pattern. They may or may not have large residuals. Influential points, however, actually have an effect on the least squares regression line, okay? So an influential point is probably going to be an outlier, but an outlier is not necessarily influential. To test for an influential point, we're going to remove that point and see if the equation of the least squares regression line changes. To test if something is an outlier, there isn't one. You just test with your eyes. You see if there's anything unusual. And that is it. We are finished with chapter 3. This is your last homework for this chapter. Okay. The homework is going to be due on the day of the test, which as of now is scheduled for Thursday. For the next couple days, we're going to do some practice, and then again, that test is on Thursday.